Before a lithium battery powers a car, stores renewable energy, or sits inside a person's hand,
What looks simple from the outside is actually one of the most carefully engineered products in modern industry.
these batteries do more than store energy. They shape movement, communication, resilience, and the speed of daily life. Trust starts with materials that are identified, verified, isolated, and recorded before production ever begins.
In battery, tiny impurities can affect safe cycle life and performance. So raw materials, the chemistry must be right from the start, because electrochemical stability is built from details too small to see. Even the current collectors matter, because every layer inside the cell has a role in carrying, storing, or protecting energy. From this point on, contamination control becomes a constant rule, not an occasional check.
This is where chemistry begins to become architecture, as active materials are prepared for even coating and stable performance.
The mix cannot be too thick, too thin, too warm, or uneven, because consistency here affects every cell that follows. The anode must be just as controlled, because charging, discharging, and long cycle life depend on balance between both electrodes. Uniform particle distribution helps the cell charge evenly, age more predictably, and resist internal instability. Once the formula is proven, it must be deposited with exact thickness across long, continuous foil without streaks or voids. Drying removes solvent and stabilizes the coating, turning a wet layer into the first durable structure of the battery. Each side of the cell is made separately, but both must later work together with near-perfect alignment. Defects must be found while the material is still moving, because prevention in line is more powerful than correction later. Battery production is continuous, but every meter still belongs to a traceable batch and a measurable process history. Calendaring adjusts porosity, thickness, and contact within the electrode, shaping how energy and ions will move through the finished cell. Compression must be exact, because too much or too little changes resistance, capacity, and thermal behavior.
The electrodes now move toward their final dimensions, where edge quality becomes critical to both safety and assembly accuracy.
A rough edge can become a risk, so each cut must be clean enough to protect the separator and preserve electrical integrity. The separator is thin, quiet, and easy to overlook, yet it is one of the cell's most important safety barriers.
Moisture is an enemy here, so some of the most sensitive stages happen in air kept far drier than ordinary environments. This is where chemistry becomes structure, layer by lane, with alignment accurate enough to support performance and safety at scale.
Some cells are stacked, others wound, but all must create a dense internal architecture without shorts, wrinkles, or trap defects.
The structure must be right before sealing, because hidden misalignment inside the cell is expensive, dangerous, and difficult to recover.
Electrical connections inside the cell must be low resistance, mechanically sound, and repeatable across thousands or millions of units. A battery cell stores energy only as reliably as the connections that let that energy move in and out under real use. The active core now receives its enclosure, a barrier designed to protect the chemicals outside.
Different cell formats demand different hardware, but every design still aims for the same essentials: containment, conductivity, and safe control.
The cell is almost alive now, but not yet. One of the most sensitive moments is still ahead. Electrolyte gives the cell its ionic pathway, making charge transport possible and turning a sealed structure into an electrochemical system. The liquid must reach deep into the layered structure, wetting the electrodes evenly so the cell can form and age predictably. Once sealed, the battery becomes an electrochemical device, but it still has to be activated, stabilized, and proven. No cell is anonymous. Each one leaves a traceable identity that follows it through testing, assembly, shipment, and service.
Now the cells begin their first charge and discharge cycles, where chemistry stabilizes and the battery starts becoming itself. Formation is slow by design, because the first cycles build the interfaces that largely define the cell's future behavior. Inside the cell, protective electrochemical layers are forming on the anode, helping stabilize performance over repeated use.
This is where early signs of good or poor behavior first appear in the data. Battery manufacturing is not only fast on automation. Some cells need a controlled correction after formation, because stability comes from managing even the byproducts of activation. After adjustment and resealing, the enclosure must again become flawless, because the smallest leak can shorten life or compromise safety.
Even after formation, the cells need time to settle, because stable products are rarely rushed at the moment that matters most.
Now the cells must show what they can actually deliver, not in theory, but in measured electrical performance. Not every cell battery systems.
Some truths can only be confirmed by looking inside the cell without damaging it.
A battery is also a barrier system, and that barrier must hold over transport, use, temperature change, and time.
Safety claims must be backed by controlled abuse testing, where cells are challenged under worst-case conditions before they ever reach a customer. The goal is not spectacle. The goal is understanding how the cell behaves under stress and whether protective design does its job.
Only after chemistry, structure, and safety are proven can individual cells move into larger assemblies.
A useful energy product is rarely one cell alone. Real-world power usually comes from
Cells must be arranged with accurate spacing, polarity, and support to manage heat, vibration, service life, and safety. At the module level, electrical continuity must be strong, repeatable, and thermally manageable under load. The module is only as trustworthy as the hidden connections that distribute current inside it.
Energy density means little without temperature control, because heat is one of the most important limits on battery life and safety.
A modern battery must not only store energy, it must also sense itself continuously.
The battery management system watches voltage, temperature, current, and balance, helping protect the pack from misuse and internal drift.
Mechanical and electrical isolation are part of safety, helping ensure that one local problem does not become a system-wide failure.
As assemblies grow larger, verification becomes even more important because the consequences of hidden faults grow with them.
The battery pack is where electrochemistry becomes a real product for transport, storage, or industrial use. By this stage, exact order matters because pack layout affects cooling, serviceability, strength, and electrical architecture.
A battery pack is also a power distribution system, built to deliver energy while isolating faults and enabling safe shutdown. Thermal management helps the pack stay within the temperature window where performance, charging speed, and long life can coexist. Protection from dust, moisture, and environmental stress begins with enclosure discipline. The pack is closing around one of the most energy-dense systems many people will ever use without seeing inside.
In advanced manufacturing, completion is not based on appearance. It is based on measured proof.
A battery pack must protect its chemistry, its electronics, and its users long after it leaves the factory. This is where the battery proves it can respond, protect, and perform as a complete system.
Temperature must stay controlled across the pack, because uneven heat can shorten life and amplify risk.
Real batteries face roads, impacts, cycling, and time, so durability has to be proven beyond the clean floor of the factory. The battery must stay stable across climates and seasons, because people use energy systems in the real world, not ideal laboratory weather. Performance alone is not enough. Products like this also move through standards, audits, transport rules, and safety frameworks.
Once validated, there's distribution as a controlled responsibility, with packaging and documentation designed for safe handling. The product is leaving the factory, but the story is not complete until it reaches the systems and people it was built to serve.
The battery becomes meaningful in the next stage, where stored energy is integrated into a network. Here the battery becomes the vehicle's energy heart, structurally integrated and electronically connected, everything the driver will later experience.
The battery must now communicate, regulate, and protect itself as part of a living machine. In another form, the same manufacturing discipline supports buildings, grids, and renewable energy systems that need dependable storage. Whether mobile or stationary, the battery must prove that it performs safely in the system that will rely on it.
This is the moment hidden manufacturing becomes visible choice, when people decide whether they trust the product enough to bring it into their lives. For the user, trust appears as something simple. Plug in, charge, wake up, and expect the energy to be there.
Powder, foil, and controlled chemistry now becomes motion without noise, daily routine without fuel.
Stored energy matters most when it quietly protects convenience, continuity, and peace of mind.
At a larger scale, lithium batteries help shift energy through time, storing power when it is available and delivering it when it is needed.
Trust is not built once. It is maintained through software updates, diagnostic thermal monitoring, and disciplined service practices.
The battery's story does not end when first use is over. Long-term value also depends on how some batteries can continue serving in less demanding roles, extending value before final material recovery.
Recycling closes part of the loop, helping reduce waste and return valuable materials to future production.
A lithium battery is never just chemistry. It is a chain of work, discipline, testing, trust, and human reliance.
This is the journey from controlled materials to dependable energy, from hidden precision to public trust.
That's it for this episode. Thanks for watching. We hope this gave you a deeper look at how real quality is made and quality and why trust matters.